Welcome everybody to this webinar for about seismic attributes and how to enhance their power. This is basically going to be a demonstration about our new GVERSE attributes product and how it can help enhance your seismic attribute workflows. But before I get into what GVERSE attribute is and what it does and how it does what it does, I just have a couple of slides, a few slides to show you, to put you in a better context of what we're talking about. And to start off, I have a slide about seismic attributes. As most of the people in the industry realize, seismic attributes have been around for a long time, and they're very, very important for seismic interpretation, mainly because they highlight features and relationships in data that are otherwise hard to notice. And I have an example of that here. So let me just turn on my laser pointer. So this is an amplitude slice through a seismic volume, time slice through a seismic volume, and this is simple amplitude data. And if you focus your attention to this area where you can see my pointer, you can see a discontinuous feature, something interesting happening here. First guess, this might be a channel, but you need a lot more analysis before you can determine if, number one, this is a channel or not, and number two, if you want to map this channel to see how far it extends into the time slice, you'll have to do a lot more analysis before you can conclusively say that. But if I were to look at the same time slice in a semblance volume, which is a seismic attribute, this is what I get. And right away you can see that that discontinuous feature highlights up very nicely as a channel system, and you can see how far it extends into the time slice, and you can see the edges very, very clearly. So that's the power of seismic attributes, that they can instantly highlight features that would require a lot of your time otherwise to be able to analyze them properly. And attributes have been around for a long time. And there are a lot of attributes, but people don't use them as much. Well, they do use them as much, a lot, but they tend to have favorite attributes. So, for example, for me, coherence is an attribute which I know detects edges, and then regardless of my data, if it's sensitive to my data or not, or maybe there are, without experimenting with other attributes, I sort of rely on coherence. And the main reason for that is the workflows associated with seismic attribute analysis are so complex and cumbersome that experimenting with attributes, trying out different attributes, different parameters for attributes, that's a big hassle, that's a big problem, which restricts people from trying or experimenting with attributes. This is a typical attribute analysis workflow that we have using existing software, traditional, which I will call for the rest of the presentation, traditional softwares, attribute analysis softwares. And let me just walk you through this. So first you have an input seismic volume. The first step would be that you identify your zone of interest and then do a frequency analysis in your zone of interest. That means you want to find out what frequencies are dominant in your data, and then so that you can do your attribute analysis accordingly. Then if you want to do if you want to generate attributes using spectral decomposition, the first thing you have to do is that for the different frequency bands that you identify, you will generate spec decom volumes. Now, that means, so I have these three frequency bands for my data, for this imaginary analysis. I have three frequency data sets, frequency bands that I identified. Now, for each of these three frequency bands that I identify, I have to generate these spec decom volumes. Now, here I'm showing it as a single square, but actually this means that, for example, if my frequency band was that I identified was from 5 to 25 hertz, and I'm generating a frequency volume after every 5 hertz, that means I have to generate amplitude and phase volumes for 5 hertz, 10 hertz, 15, 20, and 25 hertz. So that's 10 volumes that I have to generate for a very small frequency band of 5 to 25 hertz. And then I have to generate similar volumes for the second band that I identified and the third band that I identified. So already you can see the first problem of traditional attribute analysis, and that is managing your disk space. So now if I started out with a 1 GB seismic input volume, now before even I start my actual attribute analysis, in the intermediate step of frequency spectral decomposition, I have upwards of maybe even 50 times the data that I wanted. and now not only do I have to generate those volumes, which takes a lot of time, so you leave this process running overnight, maybe a couple of days, and all those extra volumes, you have to store them, you have to name them, you have to make sure that your IT department is involved in making sure that your disk space is managed, in a optimized fashion. So that's one of the problems that you get. And now once you have those volumes, all those spec decom volumes, now you want to generate attributes. Let's say you want to test out 3 different attributes. Now for each frequency band, you'll have to generate each of those attributes. So I have those shown here. So for the first frequency band, I do attribute 1, 2, and 3. Then similarly for the second band, then similarly for the third band. And now I will put these 9 attributes side by side next to each other, start to compare them, see which one actually adds the most value to my data. And if I'm not happy with the parameters of something, I'll tweak them, which means I'll have to go back, generate that attribute for the new parameters. Again, takes a lot of processing time. And then once I'm happy with, once I've seen everything and I've compared them side by side and I know which attributes I want to use, then I can go on, add them to my interpretation workflow and carry on my work from there. So and now you can see that this is a very sort of a cumbersome process, and these are the limitations of the traditional approach to attribute analysis. Number one, there's a lot of data management. Your extra intermediate volumes, your attributes that you generate, you have to store them somehow. You have to sort of involve your IT department at times if your data is very large. And then a lot of time spent on not only processing these attributes, so you have to leave them running overnight, come back in the next morning, and then start to analyze them. It also takes a lot of time to analyze it. And so that's by the analysis time, I mean that the time spent by the interpreter or the geoscientist actually loading those into their interpretation software and then trying to compare them, putting them side by side, modifying their parameters, to get the best results for their data set. So this requires a lot of processing time and analysis time on the part of the interpreter. And lastly, they are not the interpretation softwares that we have are not built for enabling efficient attribute analysis workflows, because that's not what they're built to do. They're built to interpret seismic. They're not really built to analyze attribute data. So these are the problems that GVERSE Attributes tries to address. And we try to address these problems by providing fast computation of attributes that we do on the fly. So you have your data set, and then we use the GPU, the graphics processing unit, which is much faster than your CPU-based programming, and we try to compute the attributes on the GPU on a very controlled sort of an input data, so that if you're looking at a time slice, your attribute generation will be for that time slice only, and so you don't have to generate any intermediate volumes. So even the spec decom is done on demand, so everything is done in the virtual world in your when you need it, and you don't have to have all that extra processing time and all that extra data generated for you which you have to manage later on. So we do fast computation of attributes on the fly using the GPU, and then we have an integrated visual viewer, so you can visualize your results right away without having to load your attribute volumes into a separate interpretation software. So you do your attributes, generate your attributes on the fly, and then you look at them immediately in your viewer, and that way you don't need your intermediate volumes, and you don't waste a lot of time processing the attribute volumes or analyzing them. You can do that right away. And this is what the workflow will look like. The workflow we saw on the previous slide, this is what it would look like with GVERSE attributes. So the first step is the same. You do your frequency analysis, and then the next, so these now, the square volumes have now turned into circles, and these are virtual volumes. So, and these are not, so I don't mean that you create these, you still create all those extra volumes and put them in your computer's memory. No, these volumes will be created on demand. So when you need them, this is the GVERSE Attributes application will create these volumes only when you need them, just before it is going to start the computation for your attributes, and then once it displays the results, these virtual volumes will disappear. So you do your spec decom. Again, these are done on demand, so you're not limited to 3 frequency bands anymore. You can create as many bands as you want, because like I said, there's nothing created on disk. Everything is done on the fly, on demand, and you can see the results right away as well. So once you have your frequency bands identified, you can start your attribute generation. Again, we're doing 3 attributes for each of these, and these attributes will show up right away in the integrated viewer. You can put them side by side, you can compare them, and then you can modify your parameters. And since everything is done on the fly, your results will be instantaneous. You don't have to wait till to generate the entire volume again, only to find out that your previous parameters were actually better. So you put them side by side in the integrated viewer, and then you finalize the attributes that you want, and then you generate just the attribute volumes that you think add most value to your data. And so the whole thing is, if you compare it to the previous workflow, the whole thing is much more streamlined, and you end up wasting no time at all. And something that you would do in a couple of months, a month, you end up doing it in days, or even less than a day, even at times. So that's how GVERSE attributes can revolutionize your attribute analysis workflows. So these are some of the benefits that we have. Again, like I said, the fast on-the-fly attribute generation using the GPU and controlled inputs. We have immediate feedback, which lets you visualize and compare attributes right away. Not just attributes, you can also compare parameters within the same attribute, because you have both the attributes available to you side by side. We have over 50 different attributes available. This includes our patented CAPS technique, which is how we do our spectral decomposition. But we also have additional tensor-based, geometric attributes, which are available here as well. And then we're integrated seamlessly with SizeVision. So if you're a geographics discovery user, then you can pull your data from the SizeVision interpretation directly into attributes, compute your attributes, and then send your attribute volumes directly back into SizeVision and continue with your interpretation workflow. And so with that, I'm going to now switch over to the application. And what we're going to be trying and doing is that we are going to be looking at the F3 dataset, which is offshore Netherlands. And we're going to be the problem that we're going to try and solve is that we're going to look for fault and fractures in our zone of interest, and we're going to try and narrow down 2 or 3 attributes which we think work best for this particular dataset in highlighting our faults and fracture zones. So let me switch over to the application now. Okay. Right. So this is when you start your GVERSE attributes application. This is what you see. Now, before I start, I want to make sure that I want to tell you that we support both standalone mode and integrated mode. Now, what I mean by that is, when I say integrated mode, that means I am working with the geographics discovery application. So I am integrated with geographics. I can send my data from SizeVision directly into attributes, and then when I'm done computing my attributes, I can send that output data straight back to geographics. But I can also work in standalone mode. So if I don't have geographics discovery, I don't need, I can still run my application, because we work with segY files as well. And right now, what I'm going to demonstrate to you is also standalone mode. So we're going to be completely operating in the GVERSE attributes workspace alone. So to load Seismic, I simply select the Seismic file that I need, which is the F3 block. Again, here you can see that we support both segY files and 3DX and 3DS files. So 3DX and 3DS files are the SizeVision native format for seismic data. segY, as most of you know, is the industry standard for storing seismic data. 3DX is the brick formatted seismic files, which are used by SizeVision to store seismic data. These are optimized for viewing, so you can navigate through your time slices and your inlines and crosslines much faster when you're using a 3DX file. So in standalone mode, you can still use a 3DX file, but you will need a SizeVision license for that. So if you have a SizeVision license, you can directly use a 3DX file. But if you don't, then you'll have to use a SegY file. SegY files are not optimized for display purposes. So generally they tend to have worse performance when compared to 3DX. But anyway, so I'm gonna load my file, click load. So that's gonna show up on my screen here. So now here I can see my Seismic. This is my attributes tree where I have all these different attributes that I can compute. Below which is my color palette, which shows me the color scheme that I'm using to display my Seismic. If you have a large data set, you might want to go into the area of interest dialog box where you can subset your Seismic within the GVERSE attributes workspace. So I can use this control here to drag and draw a rectangle around my area of interest. I can even use the sliders here to subset my data in time. And if you want a very specific inline crossline range and a time range, you can use these dialog boxes here to specify exactly what you need. But since this is a small enough data set, I'm just going to go set to full extents. Another interesting thing here is this attached to memory function. If you toggle this on, then what I'll do is I'm going to take all of my Seismic data and I'm going to put it into my available RAM. And now, since we do all of our attribute computation is done on the fly and we're pretty fast with it, we use the GPU to do it. But we still have to go, because we're doing it on a controlled input. Like I said, if you're looking at an inline or a time slice, we just compute the attributes for that inline and that time slice only. But that means we have to go back to disk very often and read data for the next time slice to display and then compute the attributes on it. So that means that disk I/O time still takes a lot of time, or is one of the slowest things that we have, is a bottleneck for us. So if you read your data into memory, you can avoid that as well. So I'm gonna do that now. So now all of my data has been read into memory. If you have any horizons picked, you can go to the Horizon Manager and you can click on the Add Horizon button, select your horizon file, and that horizon will also be added to your workspace. And you can see that this is the horizon that I picked and it shows up over here. Toggle the display off. I'm just going to turn it off for now. You can navigate through your volume using this control. So I can look at whatever time slice, inline that I want to look at. The number shows up here, and I can use the slider to move through my volume. I can look at any crossline that I want. Similarly, I can look at different time slices to see what they look like. And the horizon that I just included, I can also look at my data along that horizon. So this is my volume flattened along the H-curve smooth horizon that I just imported into the workspace. To compute an attribute, I just have to select the attribute from the tree, and that will be computed and displayed in this viewer right away. So we have our attributes categorized into trace-based attributes, which are all these attributes here, which include our Hilbert or instantaneous attributes. So these are done on a trace-by-trace basis. Then next we have spectral decomposition, which you can look at different spectrally decomposed volumes. Like I said, everything is done on demand, so you can look at the different components of your spectral decomposition here. Then we have our frequency-tuned attributes, which use the CAPS algorithm, which is patented and does a high resolution or frequency-tuned attribute generation. And within frequency-tuned, we have geometric and curvature attributes. And then we also have tensor-based attributes, which are essentially the same attributes as the frequency-tuned attributes, but they don't use the CAPS technique. They're computed using a structured tensor approach. And then finally, we have expression attributes, which are hybrid attributes or customized attributes where you can combine different attributes together to create one of your own. To apply an attribute, you simply have to select it from the tree. So for example, if I wanted to look at the instantaneous phase, I just select instantaneous phase here, and this is done on the fly and shown right away in our viewer. And then you can, now as I navigate through my volume, this selected attribute is computed and showed for this particular view as I move through my volume. So I can change to whatever attribute I feel like. For example, instantaneous frequency. Again, You can see the results right away, average energy, or even computationally more intensive attributes, like semblance, for example. And all of this is done, again, like I said, on the fly and shown to you straight away. So we can also, to compare different attributes, we can also put them side by side. So I can have multiple panels. I just have to add, for example, I add 6 panels here, and then I can apply a different attribute to each panel. For example, instantaneous amplitude to the first one, phase to the second one, let's go semblance to the third one, azimuth on the fourth. I can go tensor-based coherence on the fifth one. And then, like I said, we also have expression-based attributes, which is whereby you're combining different attributes together, to create a hybrid attribute, to create a customized attribute. I have one already created here called the shale indicator, where I am taking the semblance, the thin bed indicator, and the dip curvature attributes, and I'm combining them using this expression up here, and that gives me an attribute called shale attribute. I can add as many as I want simply by clicking the add expression here, and then I can add more attributes, assign them whatever attribute I want, and then in whatever formula I want. So for example, if I want to add my instantaneous amplitude and my instantaneous phase for whatever reason, I can just say x2 plus x3, where x2 is my instantaneous amplitude and x3 is my instantaneous phase. So that's how I can create my own attributes. I have one created, which I just showed you, called the shale indicator. Once I have my expression created, I can just select it like any other attribute, and it's going to be applied to my selected panel as well. So now once I have all these attributes put side by side, I can zoom in and I can look at my attributes and see how they compare with each other. And this is how I can narrow down what attributes I actually want to use for my data set. And as I navigate through my volume, all these 6 panes are synchronized, are locked together with each other. So if I switch to a time slice, for example, the attributes are going to be computed for the time slice and shown. All of this is done, like I said, on the fly, and now you can actually see how each of your different attributes looks at your time slice. We also have the disconnected mode. If you unlock the panels, now these panels will operate independently. So the zooming and the panning and even the navigation is now for each individual panel is now separate. So as you can see, I have a time slice open on panel number 2, and inlines open on others. I have a different zoom level on different panels as well. Right, so that was just a brief introduction of what the application is and some of its basic features. Now what I'm going to do is I'm going to try and show you, or try and find, which is the objective of our demonstration, which is to find fault and fracture zones for this data set, and then to identify the best attributes, to highlight those features, and to see what parameters work best for our data set. The first thing I want to do is, if you look at your seismic data, if you navigate through the volume, you can see some heavy faulting in this zone. If I zoom in here, you'll be better able to see it. You can see that this area is pretty heavily faulted. So this seems like something we should focus our attention on. The first thing we do is we do our frequency analysis. We can use these 2 tools here to do that. The first is the power spectrum. So I can select an area in my zone of interest, and I can see what the power spectrum looks like. And I can see the frequency band is from about 8 Hertz to about maybe 60 Hertz here. So that basically gives me an idea of the frequencies that that I should be focusing on. Another tool that we have called the spectrogram, which is basically where you select a trace, and then this gives you a time frequency breakdown of that trace. So this is how my frequencies are varying with depth. So as I go deeper in time, this is how my frequencies change for that particular trace. So I can look at a bunch of different traces to see what my frequencies are in my zone of interest, which is around this area. So I can see there are like 2 or 3, maybe two definitely, but maybe 3 frequency bands that I should be looking at. So this is basic help in doing your frequency analysis. And once you have your frequencies, you can start with your attribute generation. If you were following a traditional attribute software, analysis software, you'll first have to generate those spec decom volumes, for each of the frequency bands that you identify. But since we do everything on demand, we don't actually have to create those volumes. Now what I'm going to do now is I'm going to open a time slice here, because faults and fractures show up nicer on time slices, at least I think they do. And then I'm going to add a few panels. Let's add 6 panels, and I'm going to assign a different attribute to each of these panels, and then we're going to see which of those attributes actually work best. So the first one, I'm going to leave it as input data so that we have something to compare our attributes with. The second one, I'm going to assign instantaneous phase. Now, instantaneous phase is an attribute that is very good to identify lateral continuity. It's used a lot in that context. So I'm going to put that on panel number 2. And I'm going to put semblance on panel number 3, which is again another continuity measure and is very good with faults. On panel 4, I'm going to go enhance semblance, which is a new attribute that we have introduced. Presented a paper on the ACG on this topic as well. So I'm going to put enhance semblance on panel number 4. Panel number 5, I'm going to use a tensor-based coherence attribute, which is similar to semblance but computed using a different algorithm, computed using structure tensors as opposed to the CAPS algorithm used for semblance. And for the last panel, I'm going to use a tensor-based, let's say, maximum curvature, because I'm also looking for fractures. So now I have different attributes up on different panels, and now I can start to compare them. So if I zoom in here right away, I can see that instantaneous phase is not really adding a lot of value for me, because whatever I see on my input data, whatever I see on my instantaneous phase, I can already make out on my input data. So you can see here, you can see the faults here, but you can also pick them up on your input data time slice. So right away I can see that instantaneous phase does not really add a lot of value for me. I didn't have to generate the entire volume, then load it up into my interpretation software and browse through it to come to that decision or to come to that conclusion. I can simply replace it with something that I think might help me more. Let's say another curvature attribute, maximum curvature, but this time computed using the CAPS algorithm and not the tensor structure-based algorithm. So right away, you can start to eliminate attributes that you think do not make sense for your data. Again, and since all these panes are synchronized, I can zoom in and I can actually compare what attributes look like in different areas. And right here, I can see that the semblance, enhanced semblance, and coherence, these do a fairly good job of identifying these faults here, but the coherence actually is smearing the faults a little bit. The semblance is better than the coherence, and the enhanced semblance looks to be even better than the semblance. Another way you could compare these attributes is to use the maximized view. So if I were to maximize my window here, now I have the whole time slice in display in a bigger window, and then I can toggle between two attributes. So for example, I can toggle between panel 3 and panel 4, which is semblance and enhanced semblance, and I can see exactly what the difference is between the two attributes. So as I toggle between the two, I can see that the enhanced semblance is really, makes the faults much sharper compared to the semblance, which there is a little smearing of the faults here. So you can see that the faults are much sharper in enhanced semblance, but there is a downside as well. If you look at this feature here, this little curvy feature, this might actually not be a fault, it might be a channel. And if I toggle between my enhanced semblance and my semblance, you can see that the enhanced semblance sort of decimates the channel a lot more than enhanced semblance. A lot more than semblance. So semblance might actually be a better attribute to use if you were looking for channel features. But since we're not, since we're looking for faults and fractures, which show up much better in enhanced semblance is the one that we should be using compared to semblance. And again, the comparison of the two attributes was made much simpler because it was done on the fly, and both attributes could be put side by side, and the results compared directly. We didn't have to generate the entire semblance cube and an entire enhanced semblance cube to be able to come to this decision. Another way we can compare different attributes is to use the secondary attribute feature. So you have, for example, this. I can draw a rectangle on top of any attribute that I have displayed. By default, it's going to show me input data. I can play with the transparency, all right, to get it more transparent. Now this is sort of, I can see how my input data, which is my overlaid attribute right now, and my enhanced semblance, which is my base attribute, how these two relate. And you can see the amplitude sort of bounded by these faults, and I can move my rectangle around to see how my input data and my enhanced semblance relate. I can assign any attribute to this overlay rectangle. So I could, if I wanted to look at what my enhanced semblance and my, for example, my average energy look like, I can do that as well. I can simply select the average energy attribute from over here, and I can play around with it. Similarly, I can change my base attribute as well. If I were to change it to, for example, instantaneous phase, to see how my phase and my instantaneous amplitude relate to each other, I can do that as well. So basically, you can combine any two different attributes, and you can look at them using this secondary attribute view. I'm going to go back to enhanced semblance for this. Okay, so yeah, you can go back to our multi-panel view. The secondary attributes that I showed you in maximized view can also be applied here. So I can apply a secondary attribute polygon or a rectangle to any of the windows, and so you can have multiple attribute windows showing multiple overlays as well. Anybody who has worked with attributes will also know that color palettes are very, very important. So for each window, if you click the show height button, you have the color palette range shown here, and then you can tweak this, play with it to highlight features that you're interested in only using this histogram control. You can also use the color palette control in the bottom left to have more control over the colors that are shown. You can even change the color palettes from over here. And if you want to go back to your default palette, you just have to click this use default palette button, and it's going to restore the image to its default color palette. Okay, so so this is how you compare your different attributes. So we compared, we saw immediately that instantaneous phase was not really helping us. We compared semblance, enhanced semblance, and coherence, and we saw that enhanced semblance was actually the best measure amongst those. And then when we look at the curvature attributes, we can see that in this region, the curvature attributes is giving us certain information that is not very, very clear in either of the coherence or dissimilarity attributes. So you don't see these features here in the semblance or the enhanced semblance or the coherence. So you can see that curvature attributes are actually also adding some value. And when you compare the maximum curvature from caps and the maximum curvature from the tensor-based attributes, you can see that in this case, the tensor-based maximum curvature is actually working better than the caps-based tensor, the maximum curvature attribute. So we can see that for our data set, the caps-based enhanced semblance and the tensor-based maximum curvature actually help us identify the different faults and fracture areas. So we've narrowed down from all the different attributes that were available. We've narrowed down our search to 2 attributes, and now we're going to try and find different parameters for each of these 2 different attributes. To do that, what I'm going to do is I'm going to this top row, I'm going to assign all of these the enhanced semblance attribute, and then I'm going to assign different parameters to each of these different windows, and to see which parameter set works best for us. On the bottom row, I'm going to assign the other attribute that we like, which is the tensor-based maximum curvature, and then we're going to play with the parameters to see which one actually works best for us. Right, so the first window, I'm going to leave it as default parameters. This is the default parameters shown here in this pane. The frequency range is 8 to 64, which was, again, based on the frequency analysis that we did. A radius of 1 and number passes 1. So I'm going to leave the first pane as default parameters. On the second one, I'm going to narrow down the frequency range to, let's say, 20 to maybe 60, which seemed to be another, when we looked at our spectrogram, it seemed to be another frequency band that we were interested in. We can change the radius to 2. Number of passes we can also make 2. And you can see that as I change my parameters, the results are computed and displayed in panel number 2 on the fly, and you can right away see how your choice of parameters is affecting your data. Here, let's make the frequency range even smaller. Let's go down to maybe 44, increase this to maybe 24. Let's leave the number of passes at 1 and change the radius to maybe even 3 and see what it does. So basically, you can see that this is maybe, destroyed our enhanced semblance a little bit. This one seems, the faults seem much sharper than even the default. So maybe panel number 2 is the best parameter set for our data set. Similarly, for maximum curvature, we can try to tweak our parameters. Let's leave the first panel in our row as default parameters. For panel 2, I'm going to increase the spatial smoothing, increase the time smoothing a little bit, see what it does to my results. For panel 6, I'm going to decrease the spatial smoothing even more, increase the time smoothing to see how that affects my results. And as you can see, as I move my slider, you can see, if you look at the bottom right panel, you can see the results are computed directly, and you can see the effect of increasing the time smoothing or changing this particular parameter and how it affects my data. And once I've narrowed down my parameters, so for example, let's say I like panel number 2, which is at 20 to 60 hertz with a radius of 2 and number of passes 2 for my enhanced semblance, and this last panel for my maximum curvature, which is spatial smoothing of 0.8 and a time smoothing of 6.4, I can go to this parameter panel and hit the Save Parameters button for each of these, and now this will associate this set of parameters with the enhanced semblance attribute and this set of parameters with the maximum curvature attribute. And when I go to generate my volumes, I can specify this parameter set, and I can generate volumes for my desired parameters. To do that, I'll just go to generate volumes here. Here I can specify where I want to save my volumes and then what volumes I actually want to generate. So like I said, we liked our enhanced semblance, so I'm just going to select that from the tree. I'm going to click enhanced semblance, and from this drop down, I'm just going to use the save parameters option. And if I click the 3 dots, I can see what parameters I'm talking about: the frequency range of 20 to 60, radius of 2, number of passes 2. So this is what I'm going to be generating. I also liked my maximum curvature, tensor-based maximum curvature, so I'm going to select that as well. Again, save parameters, and I can look at what parameters I want to use, and which was a 0.8 spatial smoothing and 6.4 time smoothing. And I can, so these were the 2 parameter sets that I liked, but I can also generate as many volumes as I want. So if I were also wanted to generate my instantaneous phase volume, I can click that here. I can generate that, and the space that I need will be computed and shown here. If I want to add postfix and prefix, I can add those here as well. And once I'm done selecting all the different volumes that I want to generate, I'll just click generate, and that's going to generate my volumes for me. So once this process is complete, I'll have those volumes available, and I can then load them into any interpretation software that I want and start my analysis. So basically, you saw that that's what we took our data set, we computed different attributes on it, we selected the attributes that we liked, and then we had to generate volumes for only the attributes that we know will add value to our data set. We didn't have to, all the experimentation, all the tweaking of the parameters was done within the application with the help of the integrated viewer and the fast on-the-fly attribute computation. And then we ended up with no intermediate volumes, we ended up with no extra data, we spent the minimum amount of time needed, and we had to generate volumes, and at the end we generated volumes only for the attributes that we know add value to our data set to help solve the problem that we're trying to address. So that brings the demonstration to an end.